Okay, welcome everyone. Happy Wednesday to you. I hope your week is going well so far and that chemistry is going well for you. I see a couple of questions here on the chat. There's no Hayden McNeil this week, so that's next week. It depends on the kind of lab. This week we're doing the Logger Pro. Let's see, there is no class on Monday, right? Because Monday's Labor Day, so keep that in mind. And I think that's most of the questions there. Okay. Let's see, are there any other questions? If you have a question, please raise your hand. Any other questions? Okay, I don't see any. So, oh, there's one. Amanda?
Hi, how do we get the enrollment code for the Hayden McNeil?
You know what? I'm going to have you ask your lab instructor about that. So that's not until next week. You won't have to have it all enrolled, but please indicate any questions for lab. Your lab instructor is really the pro at the lab. So I'm going to have you contact your lab instructor with those types of questions. Okay?
Okay, sounds good. Thank you.
Thank you. Other questions? Okay. For the lab tonight, the live Zoom lecture is from 5 to 6. You don't have to be there because it'll be posted on the Canvas website shortly thereafter. Okay, so you'll be able to rewatch it at that point. For the lab itself, you go to your lab section. That's also your lab section is based on your CRN number, so look at the Canvas homepage for that as well. All right. All right, let's get started here. A couple of quick things. We're now sort of a week and a half into the class. You got an idea for how the class works. Let me just encourage you, it's very important to stay caught up, right? So you basically have 5 assignments a week, right? You have a pre-lab lecture, post-lab lecture for both labs, and then you have a problem set, okay? It's very important to stay caught up in this class. If you fall behind, things are going to stack up on you and it's going to be hard to get caught up again. Why do I do it this way? Well, remember at the very first lecture, I talked a little bit about how we learn. And this class is designed, right, for you to maximize your learning. That's what I want to happen, right? So remember the recall effect. You learn when you're forced to recall information, right? When you're forced to apply it. So that's why I ask you questions during our lectures, right? That's why I have questions embedded in the videos and after the videos, right? You learn by doing, you learn by recalling, right? Remember also the spacing effect. You learn better when you space out your learning rather than try to cram it all into a short period of time, right? So that's why I have these 5 assignments a week to keep you going all along the week. You learn a little bit, takes a little bit of time for your brain, your neurons to rebuild and settle, and then you can learn a little bit more on top of that. And that's a very effective way to learn, right? So that's what I'm aiming for here. My goal is for you to learn chemistry and to know what you need to know by the time we're done this semester, all right? My goal is for you to be successful, and that's why I'm implementing these things. But these things will only work if you can keep up with it, right? And if you keep up with it on a regularly scheduled basis. So make sure you keep up. Also, believe it or not, you know, our first exam is not that far away. If you look at your schedule, you can see that it's coming up on September 21st. I know that's still far off into the future, but it'll come faster than you think. The way to study for chemistry exams is not to study the night before the test a lot, right? You can't do well on a chemistry exam by trying to learn everything the night before the exam, right? What really matters for your success in that exam on September 21st is what you're doing now, right? Are you keeping up right now? Are you staying with it? Are you learning things on a daily basis? Are you learning to solve problems, right? That's what's going to be important for that exam on September 21st. What you're doing now is going to be much more important than what you do the night before the exam. I kind of think about a chemistry exam kind of like running a marathon, right? How do you train for a marathon? Do you run a marathon the night before the marathon?
No.
Right? You don't run a marathon the night before the marathon in order to train for a marathon. You start several months before and you train daily, right? That's kind of how this class is, right? In fact, if you're running a marathon the night before the marathon, you kind of take it easy, right? You don't really train much as you get close to the marathon because otherwise you'll be too tired on the day of the marathon. You can kind of apply the same thing to this, right? If you stay up all night studying for this exam that's coming up on the 21st, on the 20th, you're not going to do very well on the exam because you're going to be too tired. You got to be able to think and reason. These exams are going to be timed. They're going to be on Canvas, right? And you got to go through the questions fairly efficiently. You got to be able to think clearly. So you got to be well rested, right? So what matters for success on that exam is what you're doing right now. So stay with the program. Watch all the lectures as soon as you can if you're not watching them live. Do the pre-lab lectures. Do the post-lab lectures. Stay up with the problem sets. Again, most of you are doing this. A few of you are starting to fall behind, I notice. Don't let that happen, okay? That would be hard to catch back up. All right, let's see. Any other questions before we get going here?
I have one.
Yeah.
Do the tests, do they use Proctorio?
I will not be using Proctorio.
Oh, okay, good.
Okay. You'll also be using, your exam is not the biggest part of your grade. There's going to be a pre-test as well that you take on mastering chemistry. And that's going to count as well. So there's a lot of different parts of this grade, right? And I'm trying to make it so that all the grade is not concentrated in the exams, all right? So there's a lot of different parts of this grade. The exam will be a 1-hour exam on Canvas that you take. It'll be timed. It'll be fairly quick in terms of the timing. It'll count, I think each exam is worth something like 7 or 8% of your grade. Okay, I see a hand. Let's see, Skylar. Skylar, do you have a question?
Yeah, are there any other like practice problems that we could do besides the ones from the problem set?
Sure, yeah, there are. If you look on the Mastering Chemistry website, there's a student study area, and there's a lot more things there you can work on, including more practice questions and things like that. Okay?
Yeah, thanks.
Any other questions? Sophia.
There was an assignment on Canvas. It was like Introduction to Mastering Chemistry,
Yeah.
and it was worth 10 points, but I'm not really sure like what we were supposed to do to receive the 10 points.
You know what? That's a mistake. If you see that, just ignore it. It's for some reason Canvas is acting up and it's bringing that back on over and over. But it's not worth any part of your grade, so you can just ignore that. Amanda.
Okay. Yeah.
Hi, would you be giving us study guides for the exams?
We'll be doing a review before the exam, and you'll also have the pre-test as a way to prepare for the exam.
Okay, awesome.
Megan Buddy. Megan, are you there?
Sorry, yes, I had to unmute myself. I noticed in the chat, and I had this question too. Is there any way for us to show our work to get partial points, or is it just solely if you get it wrong, it's wrong?
Unfortunately not. It's all multiple choice, and so you'll get credit only if you get the right answer.
Okay, thank you.
Any other questions? Okay, great. So let's go ahead and get started. Again, if you have a question, feel free to raise your hand using the raise hand feature, and I will answer your questions as we go along. Okay. Let's see here what happened to my. Why did it do that to me? Hold on for a second. I'm sorry, I had some technical problems. There we go. Okay. I have multiple monitors here so I can monitor a bunch of different things at once, including one monitor that has all your beautiful faces on it. So that way I can kind of gauge reaction and see what's going on, and that actually helps me a lot. So thanks for having your cameras on. I know some of you don't want to have your cameras on. That's fine. But I sure appreciate those of you that have your camera on, and it helps me to kind of see your reactions and see your heads nod or nod yes or no, because I'd rather have you all in a classroom, right? I'd rather be there live and just be able to see you and meet you all. I really don't like this near as much, but it's the way it is, right? So here we are. Okay. Let's see. You can see my screen, yes? Okay, so let's see. At the end of last time, if you remember, we had kind of talked a lot about the early ideas of matter, right? We talked about the particulate nature of matter and the discovery of the atomic theory, right? And then we delved into the atom and we learned about its different parts, right? And how the atom was structured, right? In terms of having a very dense nucleus, right? That's positively charged, and then the electrons sort of in a diffuse cloud around the nucleus, yeah? And those electrons are negatively charged. We learned about those particles, we learned about isotopes, right? And we learned how to specify isotopes using isotopic notation, yeah? And then we got to trying to make sense of the different elements that exist, right? So we got to the periodic law. And remember in 1869, a Russian chemist by the name of Mendeleev saw a pattern that other people hadn't seen, right? And this pattern he saw was related to the properties of elements, right? And he said that when the elements are arranged in order of increasing mass, certain properties recur periodically, okay? Again, I can't emphasize this enough. Notice the progression, observations on properties of elements that were made by a bunch of different scientists, yeah? And then a law, Mendeleev came up with a law to explain, to summarize those properties, okay? The next step would be to develop a theory or a model, all right? Right now, we don't have a theory or a model that explains this, but we will get to it. The model that explains this law is the quantum mechanical model, all right? And we'll get to the quantum mechanical model later on in the semester, right? But for now, we're just gonna talk about the law, the periodic law, right? And remember last time we saw this, we saw that elements with similar properties recur periodically. And if you put those into columns, you can make a table like this, right? And that table turned into the periodic table, all right? Which we use all the time now, okay? So let's learn a little bit about the periodic table. First of all, there are some broad divisions in the periodic table. So everything that you see listed here in this sort of gray color are metals, all right? So metals. So they're found sort of on the left side of periodic table, okay? Metals have certain properties, right? They are, let's see, they are good conductors of heat and electricity. Okay? They are ductile and malleable. Ductile just means they can be drawn out into wires. Malleable means they can be pounded into sheets, right? But the most important property for right now that you really want to focus on is they tend to lose electrons in chemical reactions. And this is my shorthand notation for reaction, so I'll be using that throughout the semester, okay? So some good example, you're familiar with many metals, iron, gold, silver, copper, right? These are all good examples of metals. They all fall in this part of the periodic table, all right? On this part of the periodic table, on the upper right, are the nonmetals. Okay, nonmetals don't really have as uniform properties as the metals, all right? So they have a lot of varied properties. Some of them are gases at room temperature, some of them are liquids, some of them are solids, but they tend to not be good conductors of electricity. They tend to not conduct electricity, okay? And unlike the metals, which tend to lose electrons in chemical reactions, nonmetals tend to gain electrons in reactions. Okay, they tend to gain electrons in reactions. Okay, and sort of in between in this region right here, you guys can see my little pointer, right? When I point at things on the screen. Awesome. This area right here, these are known as the metalloids. And they're kind of in between the metals and the non-metals. All right, they have mixed properties. So mixed properties. But these elements right along here, you can see silicon is here, germanium, arsenic, antimony. These are all very important these days because they are used in the semiconductor industry. They are used as semiconductors. And that's because they're kind of in between a metal and non-metal. Remember, metals conduct electricity very well. Non-metals tend to non-conduct electricity. With semiconductors, you can kind of control whether or not they conduct electricity, okay? And that's why they're so useful, all right? And we're not going to talk a lot about that in terms of details, but that's what's happening with those semiconductors, and that's what's in all of our computers and phones and chips and all that kind of stuff, okay? Very good. All right, let's see. Let's go on. We can also divide up the periodic table into main group elements. Main group elements, that's these here that you can see in yellow, all right? And main group elements tend to have properties. Main group elements tend to have properties that are predictable based on their position in the periodic table. Properties are predictable based on position in periodic table, right? And then here in the middle part of the periodic table, we have what are called the transition elements. And their properties are not as predictable. They are all metals, so we can know that about them, but the patterns aren't quite the same and not quite as predictable as we have in the main group elements. Okay, can everybody hear me okay? Yeah? Okay, yeah, if I just got one of those messages, your internet is unstable, but hopefully we're okay and you guys can, it sounds like you guys can hear me, so that's good. Okay, what else? So main group elements here, transition elements here. And then every column in the periodic table is known as a family or group, okay? Columns in the periodic table are known as families or groups, okay? And elements that fall in a column tend to have similar properties. Right? For the reasons we talked about earlier, that's the way that Mendeleev put together his periodic table, all right? Again, for now, we don't understand why they have these similar properties. Right now, basically the periodic table is based on the periodic law, right? The periodic law is just basically says that these elements that fall in columns have similar properties, but it doesn't say why, right? We're gonna find out why later when we get to quantum theory. Okay, because remember, models give us the why, and laws just tell us what happened, a summary of what we actually see. All right, so we'll get to the model later that explains it, but for now, we're just going to accept it as at face value. Every row in a periodic table is known as a period. All right, and so you can see this is period 2, this is period 3 and 4, and so on. All right. And again, we'll learn more about those later on when we start looking at models, okay? Let's see, what else do I want to say? There are some important groups in the periodic table that I sort of want you to be aware of, all right? One of the most important ones is over here on the right. Those are the noble gases. They happen to be very inert. And by that, I mean that they are unreactive. They don't really react with much of anything, okay? And that's why they're called the noble metals. They just stay as the metal. Sorry, that's why they're called the noble gases. They just stay as that gas. They don't react to form compounds very much, all right? Other important groups that you should know about are these group 1 metals right here, lithium, sodium. Those are called the alkali metals. Group 1A, all right? And they are among the most reactive metals. Okay, this group right here, group 2A, are called the alkaline earth metals. Also very reactive. Not quite as reactive as the group 1, but still very reactive, all right? And then on the other side, you have group 6A, is called the oxygen family. And then over one column, you have the halogens. Group 7A. And the halogens are among the most reactive nonmetals. All right. So just a quick little tour around the periodic table, right? Alkali metals, most reactive metals. Alkaline earth metals, a little less reactive, but nonetheless pretty reactive. Over here, the noble gases, completely inert, very unreactive. Over here, you have the halogens, the most reactive nonmetals, right? And then the oxygen family, which is a little bit less reactive than the halogens, but still fairly reactive, okay? Those are the important families that we really pick out and give names to, okay? And we will talk about them more, okay, as we go along. Let's see. All right. Audio okay now? Everyone can hear me okay? All right. All right, very good. Let's see, remember last time we talked a little bit about ions, right? And it turns out that the periodic table can help us predict the charges of ions, all right? So if you have a metal, remember metals, what did we say about metals just a minute ago? Metals tend to do what in chemical reactions?
Lose electrons.
Lose electrons, right? So if they lose electrons, they form positively charged ions, yeah? And then a non-metal tends to do what?
Gain electrons.
Gain electrons, right? So they're going to form negatively charged ions. And the nice thing about the periodic table is it helps us to predict for a number of metals and non-metals what the charges of those ions are going to be, all right? So I'm just going to show you the table here with the ions superimposed. Notice the group 1A metals tend to form ions that have a 1+ charge. Group 2A, 2+ charge. Group 3A, 3+ charge. These are all metals, right? Because they're on the left side of the periodic table. So they form positive ions, yeah? Over here on the right side, we have the nonmetals, and notice they tend to form negatively charged ions. Group 5A tends to form ions with 3- charge. Group 6A, 2-. Group 7A, 1-. All right? And we can remember this with this idea that a main group metal tends to lose electrons and form a cation with the same number of electrons as the nearest noble gas. So if these are the noble gases, for example, and here's fluorine, right? It will form a negatively charged ion. We know that because it's a nonmetal. And it'll gain an electron, so it has the same number of electrons as the nearest noble gas, right? Similarly, oxygen will gain 2, so it has the same number as the nearest noble gas, and so on, okay? Metals would tend to lose electrons, so they have the same number of electrons as the nearest noble gas. So lithium will lose an electron, so it has the same number of electrons as helium up here, okay? Anyway, this table right here is in your book, and I would like you to make sure you know this table. You should be able to predict the ions formed by all of these, okay? So this is a table. You either have to remember this rule or just memorize this table. Okay, it's pretty straightforward. 1A is +1, 2A is, sorry, 1A is 1 plus, 2A is 2 plus, 3A is 3 plus, and then 5 is 3 minus, 6A is 2 minus, and 7 is 1 minus. Okay. All right, good. Let's see. Any questions on any of that? Let's see, Taylor.
Yes, with the periodic table,
Yeah.
the most reactive columns, they have a negative or a +1 charge. Does that have to,
Correct. Yeah.
does that have anything to do with like how reactive they are, or is that just?
Not really necessarily. It is related, but not in a real direct way. We'll learn more about why that is a little bit later when we look at the model that explains this. Okay, when we look at quantum
Okay.
mechanics, we'll understand it better.
Okay, so later on, okay, but just memorize it now, all right?
Now, for right now, we're just going to memorize it, and because we're not going to get to the model until a little bit later, and that model then will really help you to understand why. But remember, observations are just looking at the world. Laws summarize a bunch of observations, but they don't really give us the why, right? It's models or theories, right, that give us the why. So, and we've already come across our first model, right? What was our first theory that we came across already in chemistry?
Periodic theory? Oh, wait, no.
The atomic model.
Oh, the atomic model.
The atomic model, the atomic theory, right? The idea that matter is ultimately particulate, right? That's a model for the world. It says, look, the world around us is this way. It's made of small particles, right? Tremendously powerful idea that explains so much of what we see, right? We're going to be, again, we're going to be looking at many models this semester, right? We're going to be looking at the quantum mechanical model that helps explain exactly what you're looking at right now, right? In terms of those charges. We're going to be looking at chemical bonding models that explain how atoms bond together to form molecules, right? In fact, we're going to look at 3 different theories for chemical bonding, believe it or not, okay? We're going to look at theories for gases, kinetic molecular theory of gases that explains a lot about how a gas behaves, right? These models or theories, right, are powerful pieces of scientific information because they give us the why, right? And so in some ways they're the most fun, right? I mean, people sometimes think of scientists sort of as these, you know, sort of a boring person that's just writing down numbers all the time, right? Or something like that, but that's not really true. The scientists that came up with these models were intensely creative people, right? Much like an artist, right? An artist sort of looks at the world and tries to create something on a canvas or in sculpture that somehow captures part of that world, yeah? Scientist does the same thing, right? They look at the world and they try to create a theory or a model that somehow captures part of what that world is, right? And that's not a process that is just, you know, sort of dry and falls out of nothing or falls out of measurements, right? It takes immense creativity. It takes seeing patterns that other people have missed. It takes creating something that other people didn't, right? And so the scientific enterprise itself is super exciting and super creative because of those things, right? And oftentimes we don't see it that way, but it actually is true, right? Okay, any other questions before we move on? All right, let's keep going. Let's talk about a little bit about atomic mass. So atomic mass is the average mass of an atom in a naturally occurring sample of an element. Okay, the average mass of an atom in a naturally occurring sample of an element. And usually the units that we use are AMUs, or atomic mass units. Okay. Now remember, a naturally occurring sample of an element has all of the atoms that are in that sample are all atoms of that element, right? So if we have, for example, carbon, right? We have a naturally occurring sample of carbon like you do have in your pencil, let's say. Your pencil has graphite in it. That's carbon, one form of carbon. Or if you have a diamond, the diamond is also carbon. It's a different structure, right? But those are all carbon atoms. So those are naturally occurring samples of elements, right? But if we were to look at the carbon atoms in either graphite or in diamond, they wouldn't all have exactly the same mass, right? Why? What did we talk about earlier?
Protons.
The protons are all every single carbon atom has the same number of protons, so it's not the number of protons that make the difference.
Different number of neutrons.
Different number of neutrons, right? There's different isotopes for carbon, right? So not every single carbon atom in a naturally occurring sample has the same mass. Why? Because there are some that have 6 protons and some that have 7, right? Some that have 8, so they have different masses. So how do we come up with a mass for a carbon atom? Well, we get an average mass, right? Kind of like we say, okay, we weigh the masses of each isotope by the percentage of that isotope, and that gives us an average mass, right? So this number that you see in the periodic table underneath the symbol for each element is the atomic mass for that element, right? And notice it's for chlorine, it's 35.45. That means that on average, the chlorine atoms weigh 35.45 AMUs, right? Are there any chlorine atoms that weigh that amount?
No, because they're discrete.
Right. It turns out that for chlorine atoms, there aren't any that weigh that amount. Why? Because that's an average mass, right? It's kind of like if I took the average mass of all of you students, right? And I came up with some average, 142.7. Is there any one of you that weigh 142.7? Well, maybe, maybe not, but probably not if we took an average that was accurate enough, right? It would just be an average. So the average does not correspond to the mass of any individual atoms. It's the average of the collection, yeah? And here's how we calculate it, okay? The atomic mass is equal to the fraction of isotope N times the mass of isotope M, the sum of the fraction of isotope N times the mass of isotope N. So basically, what this means, this summation sign, what we mean by that is that you have the fraction of isotope number 1 times the mass of isotope number 1 plus the fraction of isotope number 2 times the mass of number 2, right? And so on, right? Depending on how many isotopes naturally occur, okay? So we can best see this, I think, with an example. So let's do an example. So a naturally occurring sample of silver contains these 2 isotopes, silver 107 and silver 109, all right? And silver 107 is 51.84% of the atoms, and it has this mass. Silver 109 is 48.16% of the atoms, and it has this mass. So we would calculate the atomic mass for silver equal the fraction of isotope 1. Okay, so this is percentage, not fraction, okay? So we got to convert that to the fraction. So in other words, a decimal value, right? So we move this over to the left 2 places to move from percent to fraction, all right? So that's 0.5184 times the mass of isotope 1, 106.90509 AMUs, right? Plus the fraction of isotope 2, 0.4816, right? Times 108.90476 AMUs, right? And if you add that together, if you multiply these two, you get 0.4816 AMUs. Notice that this has 4 sig figs and this has 1, 2, 3, 4, 5, 6, 7, 8 sig figs, but we're limited by 4, so we're going to keep it at 4 right here. I did that wrong. Should be, that's the wrong number. This is, actually, I don't have the individual results for you, unfortunately, but it doesn't matter. But if you multiply this by this, you should get 4 sig figs. You multiply this by this, you get 4 sig figs. And the total answer comes out to be 107.87 AMUs, okay? I should really, let me get those intermediate answers for you so you can see the sig figs point.
I have them, Tro, if you want me to rattle
Oh
them
yeah,
off.
great. What are those intermediate answers?
Okay, so for the first one, it's going to be 55.04196 AMU.
4196 plus.
And then for the second one, it's going to be, hold on. Hold on. Just got it. My calculator here. Hold on. Darn it. Why did it simplify that?
Yeah.
Okay, 52.44585 AMU.
Okay, perfect. Thank you.
Sorry, it simplified it, so that's why it took me a second.
Okay, so does that work out? 55. Mm. Hold on for a second. 55 point, oh, I see, 55 point. Try this again. It's actually 55.4196, okay, plus 0.4816. Sorry, I got lost a little bit in the translation there. One. 50, yeah, that's right. Okay, so that's right. 50, I just want to double check it. 4485. All right. So what I wanted to show you here was just sig figs, right? So if you have 4 sig figs here, 4 sig figs here, and more here, how many should you have here in this in this answer?
4.
4, right? So that should be 55.42. Yeah. And then this one, again, 4 and a lot more. So how many should you have?
4.
4 as well. So 4, 5. Okay. Now, so it's important to understand that you have 4 sig figs and 4 sig figs here. Okay. When you add these together, you should add the unrounded number so you get the unrounded result. But it's important to understand that you only have 2 places of the decimal, right? Because when you have addition, what do you get? You get places of the decimal. That's what you focus on, right? So that comes out to be 107.87 AMUs, and that's how you end up with 5 sig figs. All right. Not a big deal, but anyway, that's the way that works. Does that make sense? Sorry, I totally crossed that out there. Okay, great. All right, let's see. So let me have you do one. So you go ahead and do one now, and I'll start a poll here. And you do the same thing here for a different element. Okay, try to finish that up in the next 10 seconds or so. Okay, 5, 4, 3, 2, 1, 0. Awesome. It looks like almost all of you got that. The correct answer was B. Oops. The correct answer was B. Don't have it here in my presentation, but that's okay. The correct answer was B. A few of you here put A. If you put A, your mistake was not converting it to fractions, right? So when you do this, you got to write 0. Let me just stop that and close that. You got to write 0.1998 times 10.013 plus 0.8002 times 11.009, right? Don't forget to convert those percentages to fractions, right? And if you add that together and you sum it all up, you get 10.81 AMUs. Okay? Any questions on that? Okay, Michael.
Hey, I just wanted some clarification because when you did the previous problem, I thought that I saw you take the each figure from each multiplication side of the addition problem, right? So, and then using those sig figs to judge the addition problem that you were left with at the end, and judging the digits that you were given. So in other words,
Yeah. So
the
let me give you the intermediate answers here. The intermediate answers would be 2.00059, and you'd have 4 significant digits. So you could underline that one as your 4, and then
right,
that plus 8.8094, and you'd underline that one as your least significant digit, right? So if
gotcha.
if you add that together, that adds up to be 10.8099. Now you look at places of the decimal, right? And here you have how many places of the decimal? You have 3. Here you have only 2, right? So how many are you allowed here?
Oh, I see. Okay.
Yeah.
I think I just missed that the other one was 2.
Right. So you got to be a little bit careful with significant digits here. Remember, for multiplication, it's always you go by significant figures, right? So you have 4 here, you have 4 here, so you have 4 there and 4 there, right?
Right.
But for addition and subtraction, you go by place of the decimal. So here you have 3 places of the decimal, and here you have. Well, sorry. Oh, what
Is
I
it also 3 or no?
What did I do wrong there? 10 point. Oh no, sorry. This is 2.0059 plus 8.809 goes to 10.80. Oh, you're right. You're right. It should be.
So I thought maybe the answer would be
Yeah.
10.10.
Thank you. You are correct. It should be 3 places of the decimal there, right? Because you have 3 there and you have 3 there.
Yeah.
So you're totally right. My mistake. So this should be 10.810 to the right number of sig figs. Good
Cool.
catch.
Right on.
Nice job, Michael. Thank you. Yeah.
Yeah,
Okay.
thank
I
you.
was incorrect. That should really be 10.81 if it's to the right number of significant figures. 10.810.
Thank you.
All right. Sophia.
Hi, for the number 2.00059, why don't you count the 59 as significant?
Oh, good question. Yeah, because you have 4 significant figures here and 5 here. So you're limited to, since this is multiplication, you're limited to 4 significant figures in the answer.
Okay, gotcha. Thanks.
Yeah. Good question. Any other questions? Okay. Very good. All right. So you might be wondering, well, how do we figure out the masses of these atoms? One way to measure the masses is with a device called a mass spectrometer. Okay, and this is kind of a schematic diagram of a mass spectrometer. And what you do is you put in so let's say you were trying to look at carbon, right? So you'd put in carbon in here, or let's say you were looking at helium, you put helium in here, whatever the sample of the element you wanted to look at, you'd put it in here. It becomes ionized, which means that electrons are knocked off of it. Once it is charged, then once you knock electrons off, it becomes a charged particle. When it becomes a charged particle, you can actually accelerate it with electrical fields. So you use some electrically charged plates to accelerate it. And then it's going to bend in a magnetic field, all right? And the amount that it bends will depend on its mass. And you can think about it, imagine like a really heavy vehicle being hit by a crosswind compared to a light vehicle, right? If they have the same surface area, which vehicle is going to be affected more? The lighter one, right? So the lighter atoms are going to be deflected more. The heavier ones are going to have more momentum, so they're going to be deflected less. And so basically what this does, it allows you to separate the sample based on its mass, right? So if you have some isotopes, let's say this element, whatever it was, has, in this case, it had 3 isotopes, a lighter one, a medium one, and a heavier one, right? And so that's how you can measure, right, the masses of these isotopes as well as their relative abundance. What you get from this is a mass spectrum. And what a mass spectrum is a graph of mass versus intensity, okay? And so you have, so for example, this is the mass spectrum of chlorine. Chlorine has these 2 isotopes, chlorine-35 and chlorine-37, at masses of close to 35 and 37. The height of these peaks is proportional to the relative amount of those atoms, right? So for example, in chlorine, right, there's more of chlorine-35 than there is of chlorine-37, right? Here's a mass spectrum of silver. Remember we looked at silver earlier, and silver was about 50-50, remember that? Okay, so if it's 50-50, notice that its mass spectrum shows, oh, okay, about half the atoms are this one isotope and about half the other atoms are this isotope, right? So notice that the atomic mass of silver is sort of in between these two, okay? Here's a mass spectrum of rubidium. What do you think? What do you suppose is going to be the atomic mass of rubidium based on this? Is it going to be, well, first of all, you know it's between 85 and 87. Is it going to be closer to 87 or closer to 85?
85. Closer to 85.
Closer to 85, why?
There's more of the, there's more concentration of the 85.
Correct. There's more of that isotope, right?
Yeah.
The percent of
that's it.
that isotope is bigger than the percent isotope of this. So in the weighting, right, in the weighted average, this one's going to be weighted more than that one, right? So its mass is going to be closer, and in fact, it's 85.47. Okay? All right. Any questions on atomic mass before we move on? Does that make sense? Okay, let's move on to molar mass. And you watched a video on this already, correct? Everyone saw the video? Thumbs up. On the mole concept, right? So you know that the mole is a unit of counting, right? Like a dozen, right? Except for it's a lot bigger. It's 6.022 times 10 to the 23rd is the number that we give to our counting unit in chemistry, all right? And that is known as Avogadro's number, okay? Now, in chemistry, we want to be able to count atoms by weighing them, right? So asking how many atoms is in a particular sample of carbon, let's say that weighs 8.25 grams, is kind of like asking how many nails are in a particular sample of nails for which you know the mass. In other words, you can count, you know, these nails, there's a lot of nails here, right? If you want to know how many nails are there, one way you can figure it out is by weighing them. It's kind of the same thing with atoms. Are you with me? So how would you figure out how many nails you have here? Well, you'd start out with the weight, the mass, right? So you'd write 3.4 pounds of nails, right? And then notice what we have right here. We have a conversion factor between what?
Pounds and dozens.
Pounds and dozens, right? So I'd write times, and how would I write this conversion factor if I ultimately wanted to get to the number of nails, right? How would I write this conversion factor? What would I put on top?
Ounces.
A dozen on top.
Dozens.
Dozen, right? So
Dozens.
1 dozen is 0.150 pound of nails. And why do I do that? Because I want the pounds to cancel, right? Now I have dozens of nails, right? But again, I want to get to what? Individual number of nails. So I need one more conversion factor. What would it be?
12 nails over 1 dozen.
Correct. 12 nails over 1 dozen. And then my dozens cancel, right? And if I work that out, I get 272 nails. Are you with me on that? So the mole concept essentially does the same thing, right? Now I have 8.25 grams of carbon, right? And I'm going to want to do something very similar to that to get to number of carbon atoms over here, okay? And basically it's going to be conversions very, very analogous to this, all right? So the first thing we need to understand is the conversion between moles and number of atoms, all right? How do we get from moles of number to number of atoms? Well, again, the mole is kind of like a dozen, right? So for example, if I want to say, okay, how many sulfur atoms in 1.35 moles of sulfur? I would say 1.35 moles times what?
Avogadro's.
Yeah, Avogadro's number, 6.02 times 10 to the 23 atoms divided by
Moles.
Yeah, perfect. My moles cancel, and I get number of atoms. 8.13 times 10 to the 20, sorry, that's wrong. Oh no, that's correct. My bad. 8.13 times 10 to the 23 sulfur atoms. All right? So that's converting between atoms and sulfurs and moles. Let's have you try one. Go ahead and try this. Here I'm having you go the other way from atoms to moles. So go ahead and try that. Okay, most of you are getting it. You're going to use Avogadro's number, right? And the question is, how are you going to set it up, right? You're converting from atoms to moles, right? So you're going to put 1 mole in the numerator, right? And what are you going to put in the denominator? 6.022 times 10 to the 23 atoms, right? So I'm going to go ahead and end that right here. You can see, again, most of you got D, which is none of the above, which is correct, because the answer is 2.37 moles, right? So when you work this out, you get 2.37 moles, all right? So the correct answer there was D. I know, a little tricky of me. Okay, good. Let's go on. Now, so that step we just did is kind of like converting, it's kind of like the second step, right? Remember, 1 dozen is 12. Avogadro's number is 1 mole, right? So that's kind of analogous to this. The other step that we have to do is this first step, right? How do we convert between grams of carbon and moles of carbon, right? How do we convert between pounds of nails and dozens of nails, right? Well, in the case of the nails, right, what did we know? We knew, right, from here, we knew how much a dozen nails weighs, right? It was 0.150 pounds per dozen. So we need to know how much a particular a mole of atoms weighs, right? And that is an element's molar mass. So the molar mass is the mass of 1 mole of an element. Okay, the mass of 1 mole of an element. Now, if I had different size nails, right? If these nails here were bigger, let's say, what would happen to this conversion factor? Would it stay the same or would it change?
It would change.
It would change, right? A dozen would weigh more than 0.150 pounds, right? If I had bigger, heavier nails, correct? Similarly, the molar mass is not the same for every element because elements have different average masses for their atoms, right? Just like nails have different average masses for nails, so elements have different average masses. So how do we get the molar mass? Well, it turns out that Avogadro's number is picked, in fact, measured, so that this statement is true. An element's molar mass in grams per mole is numerically equivalent to the element's atomic mass in atomic mass units. So, for example, these numbers that you see on the periodic table are the molar mass in atomic mass units. But Avogadro's number is picked so that if you weigh out this number of grams of any of the elements, you have 1 mole of atoms. Does that make sense? So, for example, if you have for example, aluminum here, right? 26.98. That means if I weigh out 26.98 grams of aluminum, I have 1 mole of aluminum atoms. Okay? Carbon, 12.01. If I weigh out 12.01 grams of carbon, I have 1 mole of carbon atoms. All right? And similarly, helium, if I weigh out this much helium, I have 1 mole of helium atom. So these numbers here end up being conversions. They end up being not only the mass in AMU, but also the molar mass in grams per mole, right? So if the elements were nails, right, this is the number you'd see on the bin in terms of pounds per dozen, except it's not pounds per dozen, it's what? Grams per mole, yeah? Are you with me? And remember that as you get to bigger and bigger numbers, why are these numbers bigger for a mole of atoms? Because they weigh more. The average mass of an atom is more as you go along here, right? And similarly, if you have a dozen heavy marbles compared to a dozen light peas, right? The heavy marbles are going to weigh more, right? Even though you have the same number of both, right? So if you have the same number of all these atoms, right? The most massive ones are going to weigh more. And in this case, that's aluminum. Yeah? Okay, so let's try this. How many moles of sulfur in 45.2 grams of sulfur? So I got 45.2 grams of sulfur, all right? And then I look on the periodic table and I see that its molar mass is 32.06 grams per mole. Right? And so I can convert and I get 1.41 moles of sulfur. Right? And grams cancel. Right? So I can convert between grams and moles. All right, I'm gonna skip this question and move on and come back to our example. Now we can see how we can convert from grams of carbon to number of carbon atoms, right? What's my first conversion factor here? Well, I gotta convert between grams and moles, so I go to my periodic table, and what's the molar mass of carbon?
12.01.
12.01, right? So I write, notice I'm going to put that on the bottom, 12.01 grams per mole, right? So that step is kind of like converting between pounds and dozens of nails. I convert between mass and moles. Are you with me?
Yes.
Perfect. Now the second step then is, well, in this case, it was how many nails in a dozen. In this case, it's how many what?
How many moles are in carbon atoms?
Right. How many atoms are in a mole? 6.022 times 10 to the 23 atoms per mole. And my moles are going to cancel out, right? And I'm going to end up with the number of atoms, 4.14 times 10 to the 23 atoms, right? You see the parallel between these two problems, right? Converting from grams to moles is really just as simple as converting between pounds of nails and nails, right? Use the molar mass to get from grams to moles, and then you use Avogadro's number to get from moles to number of atoms, okay? And this calculation like this, we're gonna be doing this over and over again this semester. Okay. Javier, do you have a question?
Yes, I was wondering if Avogadro's number is based on a particular element, or why such a specific number?
Why is it such a big number?
No, such a specific. I mean, like,
Why
is
is
it?
it so specific? Yeah, good question. Yeah, because basically Avogadro's number is experimentally measured. All right. So in other words, you could take any element, right, and say, okay, if I have 52 grams of chromium, how many chromium atoms do I have? And if you had a way to measure the number of chromium atoms, you could measure Avogadro's number. And
Okay.
So it's picked so that works for every single, I mean, once you get it for one element, it's the same for all of them, right? Because it's the number of atoms in that many grams of that element.
Okay.
Yeah. Javier, you're coming to us from Mexico, right?
Yes.
Where in Mexico?
Southern Baja.
Oh, awesome.
Near Los Cabos.
Bienvenidos.
Thank you.
All right. I love that we have a student from Mexico. I think we have another student, at least one more student that's in from Europe and maybe some other places too. Later on after class, if you're from another country or in another state, stick around and let me know where you're from. I'd be curious to know. Okay. Very, very good. All right. Let me have you answer a question. Go ahead and try this one. You basically got to do the same thing here. Figure out the number of atoms in 25.0 grams of lithium. Yeah, someone asked about the molar mass of lithium. So here's a periodic table, right? And you can see the molar mass of lithium right there, 6.94. So if you're having trouble here, right, remember what we did here, right? First, convert from grams to moles using the molar mass of lithium, which you get from the periodic table, right? And then convert from moles to number of atoms using Avogadro's number, okay? And Avogadro's number is shown here, 6.022 times 10 to the 23. Nayeli, I see your hand up. I'll get to your question in a minute, okay? Oh, just put her hand down. Skylar, I see your hand up. I'll get to you. Yeah, I'll get to both of your questions in a minute. Skylar and Nayeli, just a second. Okay, I'll keep going for about 10 more seconds. Again, I really encourage you to work on these as you see them. Why? Because you learn by doing, right? I want this time to be beneficial for you. I want you to be learning. So the way you learn is by doing it, right? You got to recall it. So that's why I ask you these questions, and I really encourage you to participate. And I see most of you are, so thank you for that. Okay, I'm gonna go ahead and stop that poll now and share the results. And so the right answer is C, right? 2.17 times 10 to the 24 atoms. And the way you get to that is you have 25.0 grams of lithium. Then you're going to use the molar mass of lithium, 1 mole over 6.94 grams, right? You put the grams on the bottom. Why? Because you want it to cancel with that, right? And then now you want to go from moles to number of atoms. So you're going to use Avogadro's number, 6.022 times 10 to the 23 atoms, right? Per 1 mole. And that's going to cancel, right? And you're going to get 2.17 times 10 to the 24 atoms is the answer. Right? Does that make sense? All right, a couple of questions. Skylar.
Okay, so just to clarify, is the atomic mass of an element just the average of all the different isotopes for that particular element?
Correct. Let's see, Jane.
I was just confused on, so the reason 6.94 was in grams, because I thought it was in AMUs.
Okay, great question. So it turns out it is in AMUs. Okay, so all those numbers are atomic mass units, but Avogadro's number is picked so that it is also in grams per mole. In other words, Avogadro is picked so that any of these atomic masses in AMUs is numerically equal to the grams in 1 mole. Okay, so in other words, you can use both units for any of these numbers. You can use grams per mole or you can use atomic mass units. Both of them are correct. depending on what you're doing. Does that make sense?
Okay, and also, how do you, at the last part, how do you multiply 3.60 times 6.022 times 10 to the 23 to get that last number? Because I was just confused on what you do with the 10 to the 23. And if you can just multiply those directly.
You mean in your calculator?
Yeah, that's what I mean.
Yeah, so the way you would do that is you'd go, in your calculator, you'd go, I mean, it depends on the calculator, but 25, divided by 6.94 times, and the way it would normally work, you'd go 6.022 exponential 23. So EE on your calculator is times 10 to the 23, right? In other words, when you push that button, and again, it's different on every on different calculators, but EE means times 10 to the 23. Times 10 to the whatever number you put up here, right? So in other words, if you put, you'd write 6.022 EE23 means 6.022 times 10 to the 23. Does that answer your question? Is that what you were asking me, Jane?
Yeah, that is. Thank you.
You're welcome. Let's see. Any other questions? No? Okay. Let's see, I have 4 minutes. Let me, I know that it's not a lot of time, but let me just introduce the next topic, and then we will be ready for that next time. Let's see, slideshow. That's not what I want to do. Okay. Our next set of topics are going to be, our progress so far is we've sort of started with some basic skills, things like units and conversions and things like that. Chapter 2, we looked at atoms and elements, right? So now we have a sense for the different atoms. We got introduced to the periodic table, right? We now know how to calculate the number of atoms in a certain mass of a particular element, right? And so we know a little bit about them. And now we want to progress to the next step, which is molecules and compounds, right? So we want to begin to understand molecules and compounds. And I'm not going to say much about this today because we don't have a lot of time here, but I just want to give you a little sense for molecules. So first of all, the crazy thing about chemistry is that when you put atoms together to form a molecule, the molecule is way different than the atoms from which it was formed, okay? I mean, we already know from the very beginning of this class, we realize there's an incredible sensitivity of the macroscopic world on the stuff that composes it, right? We saw that if we change the bond angle in water, for example, we might get a totally different substance, right? So, but let me just give you an example here of what I'm talking about with the difference between the properties of elements and the properties of the compounds they compose, okay? So here you have hydrogen, right? Hydrogen is an element. It exists as a diatomic element for reasons we'll talk about a little bit later, all right? But it exists as two hydrogen atoms bonded together. It boils at negative 253 degrees Celsius, which is very, very cold, okay? At room temperature, it's a gas. Hydrogen gas is super explosive, right? If there's a hydrogen gas leak, that'd be very dangerous because if you light it, it would explode. It would combine with oxygen to form water, actually, and it's very, very explosive. Oxygen, also a gas at room temperature, boils at negative 183 degrees Celsius. Again, very, very cold to get it to be a liquid, all right? And it itself is not flammable, but it's necessary for combustion, right? But now you put these two atoms together in water, and what do you get? something way, way different, right? You get a water molecule and liquid water, which we're all familiar with. It boils at 100 degrees Celsius. It's a liquid at room temperature. And not only is it not explosive, and not only does it not support combustion, it actually is often used to take out fires or to extinguish flames, right? The point here is that when you form a compound from the elements, the compound is nothing like the elements from which it was formed, okay? Another good example is sodium chloride, right? Sodium chloride is table salt. Sodium chloride is made by combining sodium, which is a super reactive metal. If you were to put a piece of sodium in your mouth, it would burn your tongue, right? And maybe explode in your mouth. It would be very, very dangerous. Chlorine, poisonous gas. If you were to inhale chlorine, if you inhale a substantial amount of it, it would burn your lungs. We'd have to take you to the hospital, right? But you put sodium and chlorine together, you form sodium chloride, and you got a flavor enhancer that tastes good on French fries, right? Very, very different. Sodium chloride is very, very different than the sodium and chlorine from which it was formed, all right? So when elements come together to form compounds, you form something totally new and different, right? And it's one of the reasons for the great diversity of substances you see all around you, right? If we just had elements, we'd be stuck with only 100 or so substances, but you put them together to form compounds, and now we have millions of substances, right? And we see those all around us all the time. Okay, so that's where we're heading next time. Thank you for your attention. I hope you have a beautiful afternoon and a great rest of your week. Remember, Monday is a holiday, so no class on Monday. We'll get back together on Wednesday, all right? But you got a few things to do between now and then with your labs, so don't forget to go to the pre-lab lecture today at 5, or watch it there shortly after that by watching the recording of it, okay? Thank you very much. I'll stick around for a while and take any of your additional questions. But for now, that's the end of class.
Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you, Professor.